All right, everyone. Hello. Welcome to day 2 of the EPOCH workshop. Yesterday we mainly just covered things like the core EPOCH packages and the physics packages. We have a bit of an extra theme today where we're looking at sort of best practices for running, what you can do with the codes, and where EPOCH might be heading in the future. So I'm going to start with what will be my last talk. It's quite a short one compared to the others. We have a basic rundown on some of the advanced diagnostics that you can do with EPOCH. So diagnostics, probes, subsets. These are ways that you can really simplify the output of your code and to really target specific things that you want to run a PIC simulation to find. So one of the main issues, and I said this yesterday with these PIC simulations, is if you wanted to output everything, all the particles, all the positions, all the fields for every time step, that's just way too much data. You have to sort of filter out the specific things that you want to see, like number densities or temperatures. But even these can still be a bit intensive for the diagnostics, especially if you want to know actual particle properties as well. You could be running into big problems of just saying, well, I want to know the properties of some particles, but I just have to output all of them, I guess, and then just ignore about 99% of them. It's not a great way of dealing with data, so we do have ways to trim down these outputs. One of the ones we'll be talking about here, we have, let me get my laser pointer back. We have a few examples. So in the output block, you can have these things called subsets. You can also have particle probes, and these are all examples of data filtering techniques. So start off with particle probes. You can place in a simulation a special plane in a 3D simulation, or a line in a 2D simulation, or just a point in a 1D simulation. And every particle that passes that plane, line, probe, point is going to be tracked and then saved into a separate data structure, your sort of probe arrays. And you can be really specific on what you want to come through these probes. You have to identify each species which will trigger it. You'll need to pick a direction that you want the particles to pass the probe in. So it'll only pass particles going that way. It won't save them coming that way. You need a second probe for that. And automatically you will get the weight, the momentum, and the position of the particles that pass this probe, which is a very useful feature if you want to track where energetic particles are going. You can filter those particles based on kinetic energy limits. So you can say, I'm only interested in high energy electrons passing this probe, and I want to know what they're doing at this point in the plasma. That's a very good thing you can do with probes as well. You can also have it output particle ID if you want to track specific particles through the simulation, or you can let it tell you the exact time the particle passes the probe as well, if that's an important metric for you. We don't write a probe file into every SDF file. We'll only actually write that if there have been particles which have passed the probe since the last output file dump, and the output file will only contain particles that have passed since that dump. So it's not going to be every particle that's ever passed the probe. It's going to be the ones in a specific time window, which is really useful at really lowering the total number of particles that you need to dump. So here's a little example that we have for you, example 5.1 in these slides on the EPOCH workshop. We have got a output block which says we always want to output particle probes, and we have to specify the probes in different unique probe blocks. Again, you'll be able to find where all these sorts of parameters that you can set on the probe, find these on the EPOCH documentation pages in the user guide. In this example, we have a 2D simulation where we've got an electron bunch which drifts past a particle probe which we've defined. And if we look at the kinetic energy spectrum of particles that have passed that probe, you can see that it's mainly peaks around 550 keV or something like that, with a bit of thermal drift as well, which is the species that we've set up there. Something else you can do is if you want to reduce the number of particles that you're dumping, but you don't want to use a particle probe, you have other ways of doing filtering as well. You have these things called subsets. So you can define you can define an output that says, I will only want to dump particles to my file if those particles meet a few criteria. It could be if they're in a certain position window, or just give me a random sample of them so I can see what some of them are doing in my species without having to look at all of them. So you've got position subsets, you've got random subsets. So position everything past this line, or random, just give me, I don't know, half the particles, and it'll pick them randomly. So you can pick by momentum component, you can pick by total energy, or by specifying the gamma factor, the Lorentz gamma factor of your particles. And you can also use it to output regions of fields as well. So you can say, I want to know the electric field in my simulation, but I only care about it in a small region. So I will just dump that small region to file. And because you save a lot of memory by doing that, you can get far more outputs like this. It wouldn't be out of the question to have a really rapid output block, which is dumping the electric fields basically every time step using a small subset of the simulation domain. Problem with subsets, you might find, is that it doesn't save the particles that it has tracked. So if we do a subset dump, we will check all the particle properties at that time step and dump the ones which meet it. But if we were to do the same subset later, it will resample those particles and potentially pick different ones. If you want to track these same particles going through the simulation, you can use persistent subsets. You have to pick a time in your subset block, and then you say, at this point, start my persistent subset, and everything that fulfills the criteria at that time step will then be tracked later on. So an example here, we've got 2 particles. By default, if you have random sampling, one time step it might give you this particle, and then this, but maybe the 4th time step gives you a 2nd particle, and then goes back to the first one, where you don't get that behavior with these persistent subsets. Here's an example of what subsets look like for both particles and fields. So in this example, we've got an output block again, where px, the momentum in the x direction, instead of saying print it always, we'll just say print the refluxes. And refluxes is a subset which we've defined up here, which says give me a persistent subset, so always track the same particles starting at time 0, provided that they are up to this maximum x position, so everything less than x max will be saved by this persistent subset. And example 5.2 initializes a simulation in 2D, which looks a bit like this. The particles fill this space, but our subset particles only represent this slither that we've given a drift momentum to. And you can just output the phase space of those particles as a function of time with the subsets. And I've also plotted the electric field of a small window in our simulation using this target subset. So EX output, give me target. This is where we define the target subset. It has an x min of 15 up to an x max of 20, which is this region here. You can find that documentation in example 5.2. And then PIC simulations can also be really noisy as well. So you might find it more useful to print averaged quantities of your variables over multiple time steps. A good example of where we can do this is if we say, let's initialize a target with a vacuum surrounding it and a simulation window, and just look at what happens to the electric fields over time. If our target is heated, then it's going to have particles, charged particles, that's bouncing around on the inside. Some will try to escape, but they'll leave their opposite charge behind, so they'll get drawn back in. You'll set up physical sheath fields around the outside. But in a PIC code, you also get a lot of noise. And you'll also get these noise fields as well. So how do you distinguish between fields that are non-physical and noisy compared to actually physical fields, which might be in the simulation window as well? And you can do this with averaging. So you would imagine that if you have a noisy region, when you average the field in that region over time, that field will go to 0. But a physical field is going to stick around. So that's an example of what we're showing in this dump here. So this is the EY field around that simulation with and without field averaging. So when we, without field averaging, with field averaging. So when we don't have averaging, we see all these noisy fields because I've given it a really poor resolution. And you have the sheath fields above and below. But when you switch averaging on, those noisy fluctuations go away and you can see the sheath fields a bit more clearly.
Stuart, if you put a laser in there, are you not going to average out the laser oscillations of the field?
You would, yeah. So that is
kind of dangerous then.
Yeah, you need to make sure that whatever you're trying to average doesn't change much over the simulation runtime. Over the averaging window, which you can set yourself. So some care is needed there. I think it's useful for, in this one example which I've given here, I don't know how many people are just simulating, I shouldn't say neutral as a charge, a plasma block in a simulation window, but yeah, there's ways that you can get around it. Also good at looking at return current densities, because they can also be quite noisy. When you fire electrons through a solid and it draws a return current back, much easier to see that return current if you use this sort of field averaging. This is basically the same example again, but one which you can run yourself. So example 5.3 provides this averaging. EY has no averaging, but EX has the average. So when we look at EY, we can see the two EY sheath fields and some noise, but when we look at EX, we just see the sheath fields with no noise in the middle. And it's a simulation that looks a bit like that. And then you might find when you're coming to run your really big EPOCH simulations, especially if you move towards big clusters, that you can only run the job for a certain amount of time, and maybe that's not enough time to run a full simulation. So restarting the simulation will become an important thing for you to do. What you can do with EPOCH is you can set a restartable flag in your output block. You can have multiple output blocks, by the way, that output at different times. So this one only dumps every 20 femtoseconds, and it gives you a restart dump. The restart dump is literally everything that you will need to restart the simulation. It's all the optical depths of the particles, it's all their momenta, their positions, it's all the fields, it's all the currents. It is all the memory that is being held currently in the simulation. They can tend to be absolutely massive files, which can take 10, 20, 30 minutes to write, depending on how big your simulation gets. So you need to give yourself enough time to write those restart dumps if you are going to be running restart simulations. And there's a few different ways you can trigger a restart dump. I've shown here using it with this file prefix restart. Well, no, it's the restartable equals true, which is the line that creates the restart dump. And I should say, to actually restart a simulation, that is a control block variable. So you just tell it the file that you want to restart your simulation from, your restart snapshot. So you might decide to run it at regular intervals if you don't know where it's going to get to in your allotted time. Or you can have it set to run, you can force it to run a restart dump yourself as well. I'll go through a quick example. Example 5.4 is an example of running a simulation with a restart. There are a few commented outlines in the input deck which you can do on and off to have the first simulation, which goes to, say, 50 femtoseconds. And then when that simulation is done, you can comment that out, uncomment the next line with the restart snapshot, and it will go from 50 to 100 femtoseconds using the 50 femtosecond input. And we will also output the restart dumps here. Here we forced it to run up to the end and only print a restart dump on its last dump. This would be the case where, yes, I've run my simulation, I think I've run enough time, but I want to be able to check later and restart it if I need to simulate more of it later on without having to do the beginning again. So that's the use case for the force final to be restartable flag. And yeah, here's an example of what the electric field looks like in that simulation when you run it to 100 femtoseconds following the restart. It looks the same if you would just run it for 100 femtoseconds without a restart. But you will notice when you do this that restart dump is going to be much bigger than the other output files that you plot, so caution there. And this is maybe the most useful command for running restarts on a cluster, because you know how long your simulation is allotted for. You say, I want to run this job, give me 100 cores for 5 hours, say. You don't know whether your simulation is going to end in 5 hours or not, so you can print regular restart dumps and then just use the last one, or you can use this stop command. If a file with the name stop in capital letters appears in the same directory as your input deck, then the simulation will finish its current step, print a restart dump, and then end the simulation. And you can make this wait. You could create this stop file, say, after 3 hours of your 3-hour, 30-minute simulation. Give yourself 30 minutes to write the restart dump, and then you can just continue iterating your jobs like that. It's a really useful command, especially this sleep function. So sleep 60 here means wait 60 seconds, then create my stop file. And this ampersand means, well, I can start running other commands after this, and this will just run in the background. So, yeah, that's a good way of running for big cluster simulations. And I think that's basically everything I wanted to say on advanced ways of running EPOCH. So I'll take any questions on that. Joe?
Yeah, so there's the output global block, and in the output global block it states the force last file is to be restartable by default.
That's output global, I think. That's different from the output blocks, which we usually recommend, and the output blocks are in the examples as well.
Right, so as long as you haven't specified the output global block, then it won't trigger automatically the final file to be restartable.
Yeah, I don't know. Do you know much about the output global block, Tom? It's not something that I use. I think it's quite a bit of a deprecated feature.
Yeah.
I don't know. My guess is that if you don't specify the block at all, it won't default. I think if it did, you didn't have that flag in it, but then I'm guessing here.
Yeah. The other thing I wanted to mention as well is sometimes if you're running ludicrously large simulations, if you haven't allotted enough RAM on your job, then when you go to then write the stop file, or write the touch stop file to then stop the simulation, what actually happens is you run out of RAM, and then you don't end up making a restartable file at the end of your simulation. So just be cautious of that.
Okay, so cool. Right. Well, since I got your attention, I will just mention that I think yesterday I said we'll be doing something about project sort of stuff to be doing in the practical time, where you can either have a go at the 1D simulation with the laser hitting some sort of plasma target, or you can have a go at implementing your own sort of work features, and we'll come around and give you a hand. The intention of that is still to create a sort of virtual poster session in a way with laptops instead of posters. So we'll take it in turns to go around the tables, and if you want to have, say, a figure to show or an animation to have on the laptop that other people can check out and see what EPOCH can do, that'd be a good thing. I think we're doing that at about 3 maybe-ish. Should have kept the ballpark 3-ish.
Yeah.
So there's plenty of time to actually get something up and running. If anyone has any problems with running EPOCH for any particular things that they're trying to do, just give us a shout. We'll be meandering for a bit, and then a few more talks later today. Thank you. All right. Hello, everyone. So far in this workshop, I've been giving a very long spiel about how every single piece of code lines that are in EPOCH works. But that's not typically the user experience of running EPOCH. You're normally setting up a simulation and then trying to deal with the output files. You probably spend more time writing output files and analyzing them than you do actually running the code. And we have some packages here which have been developed at the University of Warwick by Ben. And he's going to talk a bit about some some diagnostics for laser plasma instabilities.
Right. Hi, everyone. So I'm kind of have like the opposite thing of, I don't really fully know how, I know how EPOCH works, but I've never actually touched any before Tran. So I'm more of like an end user looking at this thing called laser plasma instabilities. So really this is just an excuse just to go over what I've done for the last 4 years. So that's what it is. So I guess kind of split into 4 things. I'll briefly go over what I mean by laser plasma instabilities, because there's many, there's not just one. And then sort of breaking it into how would you then go about modelling it in EPOCH. A lot of it will kind of be a repeat from what Stuart's already talked about, but I guess it's kind of, he's given you all the detail, I'm giving you a sort of like how I would just use some of that detail. And then things like, what I've done in Fortran to be able to, not Fortran, Python, to observe these LPRs and so on. And then, unless I've rambled too much, I'll show you sort of an experimental comparison. So, this is a nice picture from this paper here. I can't draw very well, so. But you can kind of see here, this is your mock-up of a density profile that you get in your ICF capsule. So I look at direct drive case. So you have your fusion pellet and you fire your lasers directly at this normally plastic ablator. And when you fired at it, you create this plasma, and you normally have this inhomogeneous density profile that sort of ramps up exponentially. And you have these sort of key parts of the density ramp where you can have several instabilities growing, and they're all problematic. But the end sort of goal is to try and mitigate these instabilities so you can have as much laser intensity reaching this high part over here near a region called the critical density. So this is where your local plasma is oscillating at the same frequency as the laser, and it's in this region where you get a lot of inverse Bremsstrahlung absorption. So this is where you're trying to couple your laser energy to your target, and if you can couple as much as possible, you're going to have a good chance of achieving emission. Problem is, down over here you have lots of things that can remove laser energy. So particular ones I looked at during my PhD were things called SBS and SRS. So what happens is your laser comes in, you can produce a scattered light wave. These two light waves beat together, and when they beat together you can have electrons or ions getting trapped in the peaks and the troughs, and this creates a third wave, which could be an acoustic wave if it's ions getting trapped, or a electron plasma wave if it's electrons getting trapped. And these things are normally called three-wave instabilities, and they're all underpinned by these phase matching, and then you can solve them using the wave dispersion. And that's quite useful to do because, for example, SBS will have a different frequency compared to SRS. So when you're trying to diagnose these in EPOCH, it's good to know kind of what you're looking for. And then besides these two instabilities, the other one I had a look at was this one called two-plasmon decay. So in this case, your laser comes in and you're creating a pair of electron plasma waves. Technically this is wrong, one goes backwards, one goes forwards. But the problem with these electron plasma waves is they can be damped, and this can give energy to the electrons and create things called hot electrons, and these can preheat your fuel, and that's to your detriment basically. I haven't really got a fun name for this, but I call it sort of the matrix of doom. It's basically everything, maybe not everything, but a lot of the kind of parameters you want to know when you're modeling LPI. So for example, you kind of, again, start with the most basic thing of where are these instabilities growing. So SRS and TPD are limited to only grow up to the quarter critical, because you're producing two waves which both have a dependence on density. So electron plasma waves and electromagnetic waves have a heavy density dependence. So you can only go up to this section of the density ramp, whereas stimulated Brien scattering, your ion acoustic wave has like a sonic dispersion relation, it has quite a weak dependence on density, so you can see these instabilities all the way up to the critical density. In reality, trying to do a full simulation to the whole critical density is quite expensive, so you normally just sort of pick somewhere in this region where you can see all three. Then you kind of get into the more sort of finicky type things of these instabilities can grow in one of two ways. You can have a convective growth, so in this case you sort of have a region where your process is resonant. So going back to the last slide, we had this phase matching. Now this is only achieved at a certain point of creation. So say it was here, this is where you have your perfect phase matching. As those waves propagate, say one goes backwards, one goes forwards, your wavelength changes, so this thing is no longer satisfied. So when you have convective growth, you essentially have a region where this thing can stay resonant for long enough, and once it escapes this region, you have a finite gain. So it basically means convective instabilities can only grow to a certain threshold, which you don't want them to grow, but it's nice that they're capped. The problem with absolute instabilities, they can have unbounded temporal growth, which means if they didn't have anything to stop them growing, they could just keep growing forever. So that doesn't happen in reality. Yeah.
Just wondering about in the convective absolute row, is it meant to be the same variable on the top and bottom of the quotient for all the things?
For these things.
Yeah, because there's always n critical on top and bottom.
Well, I think again, probably not the best way that I've drawn it. What I'm trying to, what I was going to get to is that this convective growth,
it's not
it can only happen below this point, whereas when you get to the critical density, they can grow as an absolute instability. So where convective growth occurs, where the absolute growth occurs, they're at different points. So for example, if you want to then, again, model purely an absolutely growing system, you probably just want to stick to just modelling this one density.
Okay, that makes sense. Thanks.
Again, this is how my brain works.
Yeah.
My brain is very weird. So, so those are the sort of things that again you want to consider. So then obviously you've got to think, well, if I want to model this correctly, then I want to get the right sort of convective gains if I'm comparing to an experiment. So these things are dependent on your density, your laser intensity, but then also wavelength, and this thing called your density scale length. So this is essentially just a metric of how your density varies along the space. Typically, again, we do an exponential profile, and that just means your profile is some minimum density times an exponential and x divided by this scale length. Similar can be said for things like TPV, because they're both dependent on electron pulsar waves. And then this is where it gets, again, annoying, because there's even more parameters you want to think about if you're modelling all three of these things. So the ion acoustic wave, I think I said before, has a sonic dispersion relation, so they kind of travel at roughly the sound speed. But the blast off you have from firing your laser at your plastic, you have a flow going in the opposite direction at roughly the sound speed, and this can Doppler shift your ion acoustic wave. So it's your flow speed and your flow scale length that can sort of mitigate some of these instabilities. So, you want to set up your EPOCH simulation. It's not just I'll put in a density, I'll put in a some sort of laser intensity, and I'll get the right answer. You basically need quite a lot of things to get the exact picture. So, I realised there was supposed to be a slide that I'd accidentally deleted. But basically, the reason why this becomes a problem is your end goal is perhaps you want to model the whole capsule implosion, not just 20 picoseconds of it in EPOCH. A hydro simulation doesn't have all this LPI physics inherently in it, so the sort of goal would be that you could do a load of EPOCH simulations, vary a lot of these parameters, and then spit out what are my hot electrons going to be, what are my energy losses due to SRS or SBSB, and then you can then use that to get a better sort of capsule implosion simulation. And then this is where it becomes problematic, because if you were just varying one or two parameters, your machine learning model can be quite easy to train, and you don't need to do too many simulations. It becomes problematic because now you want to change density, intensity, wavelength, density scale length, polarization as well, because this can change what type of stat ring you have, both your temperatures, and then you include flow. I don't know, that's at least probably like 8 parameters you want to train your neural network or Gaussian process on. It's quite expensive. However, it's still worth doing some LPR stuff in EPOCH. again, a lot of problems with ICF come from the presence of these instabilities. So that's pretty much what my PhD was looking at these sort of things. So you don't really need to change anything in EPOCH to see LPI. It's an inherent thing that comes from the Vlasov equation. If you linearize it, you'll get these three-wave couplings in there. So you just need to set up your input deck and just let it run, and then work out how to read your data. So on the right-hand side is kind of like a standard mock-up of a kind of 2D EPOCH run that I did. So I picked sort of a density range that I could get away with simulating. So from about 10% critical to about 26%. So this covers quite a lot of the range where all three of those instabilities I talked about before can grow. Then normally from someone doing hydrodynamic simulations, they can tell me what the density profile looks like in this sort of range, which is given in red, and then in blue is my flow profile. So those are the two main things that will control how LPI grows. And kind of what a lot's been sort of said maybe today and yesterday, these 2D simulation grids are massive. So I think, for example, in this case, the cell was 38,000 long in X and 1,200 high in Y. When I went to go and output just 3 fields, density grid and a temperature grid, it's about 9 gigabytes per one. And you want to try and, these things grow at such a speed that you really want to get quite a lot of snapshots. So, your entire simulation will cost you about 7 terabytes of data. So, and that's like from being quite lenient with some of these things. So, you've got to be careful with kind of like how you set this up. So rather than just taking snapshots of the entire grid at all times, you put these things in that Stuart said called probes. So these things can help look at your hot electrons passing through certain regions. But then these dashed lines are called accumulator strips. Now, accumulators aren't in the sort of free access EPOCH just yet. They will be. But what they allow me to do is essentially just take field measurements along these lines using the subsets that Stuart talked about earlier. But instead of having to output, 20,000 files to get this time sampling, I can just do one file that stores all these 20,000 individual samples in. So I'll get onto that. But yeah, so again, when you're considering setting up your EPOCH simulations, again, Stuart's pretty much already covered this, but your initial thing is your sort of control parameters. And the main thing to try and do is, can you restrict your box to be as small as possible without losing all the key physics? There was also talk about self-heating, and one way you can try and sort of limit that is keeping your sort of number of cells in X and Y to obey this condition, which basically means you're resolving your Debye length. So you just get the formula for the Debye length, for your temperature and density and so on, plug it in, and then just work this out. Again, in reality, in 2D, trying to resolve the Debye length or lower than the Debye length is quite expensive. So typically we normally just do something where it's 20% bigger than the minimum Debye length or something like that. And it's not just a random number. It was mainly used by the fact that when I read Tony's paper, he used these slightly bigger cells, but you use higher order spline shape functions, which you can do by, when you compile your version of EPOCH, you can just put an extra flag to define that I want to use these third order shape functions. These really sort of help mitigate self-heating with even bigger cells, so those things can save you time. And then in terms of your boundary conditions, a lot of it's kind of dealer's choice, whatever works best for your problem. Only some sort of things to consider, for example, are, if anyone is doing LPI here.
So would that be n in one dimension? So you would have like n squared would be based on that, or
in this thing here.
Because you talk about in 2D a useful approach is n over n equals L over this, and I guess I'm wondering whether you would also want to whether that number of simulation cells is in total or in one dimension.
So I think in here this is just I couldn't be bothered to write nx and ny, so it's just like your number of x cells would be your length in x divided by the Debye length. Your number of y cells would be your length in y divided by the Debye length. But yeah, so your boundary conditions is again, it's up to you, but there's some caveats. If you're doing things like side scattering LPI, so this is a case where your light wave exits the simulation perpendicular to your density ramp. These can then come back into your simulation, and if you remember, I was talking about these convective growths where you only have a certain region where they can grow in. They leave the simulation, they're capped at a certain gain because they've left that resonance region. But if you use a periodic boundary condition, they can come back in, enter that growth region again, and then grow above their convective limit. So this is unphysical, and you're getting some sort of like numerical absolute growth, which isn't actually true. Again, I think I'm just rambling on because this is what I spent 4 years looking at. But then you get into sort of more things you might be interested in, so things like setting up your species. Again, a lot of this is now basically, Stuart did a much better job at describing this, so listen to him. But things like, this idea of an inhomogeneous density profile that you're looking at, and you want to look at things like, how your LPI grow at different scale lengths. You can put in your mock-up of your density profile with some exponentially growing thing dependent on the density scale length you put in your constant block. And then in terms of adding that flow profile, you can do this by just setting each of these species to have some drift momentum. So for this is an electron species, so you just times the mass by the flow profile that you want to add. So in this case, I've just said, I know what the flow speed is at one end, I know what it is at the other end, just do some linear interpolation between those two things. And if you're going to add flow, it's often useful to then add this thing called an injector. So this means that, at one boundary where all my particles are exiting due to flow, I want to put another thing at the other end, which is basically topping up my simulation with the same amount of particles coming in. So this way I don't lose any sort of mass and just, it becomes a bit unphysical. So the second thing then comes with, if you're doing ion species, one thing I learnt the hard way is if you just do an average ion model, so say you've got multiple species rather than just one, if you use an average model, you can get a lot of the physics wrong. So if you plug in, if you compute the entire kinetic dispersion relation with each individual ion species you have, you can actually have two modes that grow rather than one. You have something called the slow modes, which I've called that because they have a slower phase speed, and you can have something called the fast modes. And you might think, oh, that looks nice, but the problem is these modes have very different Landau dampings, and the growth of these instabilities are very much dependent on the level of damping you have nearby. So if you use an average model, you get this completely wrong, and you can see how dependent it is on your local conditions. So for example, if you're modelling somewhere around here where your ion temperature is about 60% of the electron temperature, it's your fast modes that have quite high damping, so you'd expect everything to be controlled by these slow modes. Alternatively, if you're at this point where your ion temperature is really low, your fast modes have pretty much little to no damping. And this means you could see things like SBS, which are dependent on acoustic waves, growing to really high levels. So, you know, if you want to model these things properly, you've kind of got to do all the nuances. In this case, instead of just doing a one species block where you call it, you know, hydrocarbon, you do a separate block where they have their own charges and masses, and then you can just define their particle per cell number based on if you want it to be a quasi-neutral plasma or something other than that.
What's the cause of the difference between the charge distinguished and charge averaged?
If you just have an average model, you just have essentially one fake ion species where it's just like your normal ion acoustic wave type thing, where it just obeys some standard sonic dispersion relation. Whereas with this, you have a weird scenario where your ion acoustic wave could be travelling a lot faster than both the lighter species and the heavy species, or in the case where it's travelling faster than the heavy species but not as fast as the lighter species, and you can't get that if you just have one species, because you don't have that distinction between what's light and what's heavy. That's my answer to it. For the sake of time, I'm going to skip this part, but these slides will be uploaded. If you want to do collisions, these things are also important for modelling LPI, so this is an example of how you could do it, but I'll skip that for now. And then again, we're getting to a part which is again very familiar to what Stuart's done. So again, modelling LPI is, you know, it's a key thing to have the correct laser profile. So there's many different ways you can do this in EPOCH. You can do it using a plane wave, which is pretty simple enough to do. Stuart mentioned yesterday you can do a Gaussian profile. So this means that your profile now has some sort of finite size. This is pretty good if you want to look at things like speckles. You know, these are normally given by some size relevant to the optics you're using. Again, you can then, if you want to focus this on a particular point, you can use a focus Gaussian profile. And I think the main goal of trying to, you know, look at these more narrower, distinct laser profiles is to model these things called speckle patterns. Now, I haven't done an EPOCH version of this because I didn't have time to actually do it myself, but this is kind of what you would see in like an experiment. You apply these things called random phase plates and things called smooth and bispectral dispersion. The random phase plate basically gives each one of your beams a random phase, and it tries to create this nice uniform illumination on your target. What happens is you end up with these sort of like regions where you have long, thin parts with varying intensity, and you can apply something called smooth and bispectral dispersion (SSD) to try and help mitigate some of these LPI. So your LPI grow on a certain time scale relate to their growth rate. If you can essentially wobble the speckle up and down at a certain time, you can help detune this instability. And how you could go about doing this in EPOCH is essentially you'd have your phase term, which is incorporating all the wavefront curvature that you had from the previous slides, but then you'd add some new terms in. So this is something called a static phase term, and these apply the random phases to each of the beams, and this thing which is dependent on what kind of optics you want to simulate. And then you have this time varying phase, which again, for the poor drawing, but it's this thing that makes it wobble up and down. So that's kind of the more advanced things you could go on to do if you want to look at LPI. And then, a bit overkill at this point, you could also do broadband lasers. So things, for example, where you're trying to mitigate LPI by having temporal incoherence from having many different wavelengths. You could do this in EPOCH by just basically having many different laser blocks. So in this case, each one of these has a different random phase. They have a different frequency, which is selected from your choice of bandwidth. You normally just samples from a uniform distribution. And then each one also has a varying amplitude depending on what power spectra you can use. You could have a flat power spectra where basically all of them will have the same amplitude. You could use a Lorentzian or a Gaussian. It's, again, completely up to you what you'd like to use. So that's, again, a lot of setting everything up. And then what you're left with, when you output your EPOCH data, it's just your field data, your density data, your temperature. How do you actually then go about seeing these instabilities grow? Well, kind of a lot of it then becomes from, post-processing. So, like I said, these instabilities all grow with different frequencies. So the first thing that's best to do is do some frequency filtering diagnostics. So eventually you're going to want to work out the intensity of these instabilities. You're going to work out point influx. So you need to filter out, for each field that you've got. So for example, this region in green, I know comes from SRS range frequencies. This region in pink comes from SBS or laser. So you can normally just do this by setting up some sort of bandpass filter. So this basically means if I choose some frequency omega 2 and some frequency omega 1, I can select a specific part of that electric field which I know is only due to SRS, or in the other case due to the laser or SBS. Normally you'd apply some sort of smoothing window to this as well, and then just do your typical convolution of whatever your field is along with your bandpass to get your new filtered field. So that's one way of doing it. And once you've done that, you've got your filtered fields. You then also got to be quite careful with how you calculate your point influxes. So I guess the best example for this is with SBS, you're creating a scattered light wave which has basically the same frequency as your laser, but it's traveling in a completely different direction. So how do you then, distinct between the two? And the answer is you use this sort of directional based point influx. So for example, you can work out point influx if it's a wave purely traveling in the forward direction, and that will give you your laser. In the opposite sense, you can work out something that's traveling purely in the backwards direction, and that will give you your SBS light. So for example, this is kind of your mark up here. The black is if you just outputted the laser point influx on its own. The red, you can see, is if I just plot the incoming laser, and you can see, that matches what I expect. That at some point, initially it's not on, and then after 1 picosecond I'll let it ramp up, and I've just got this laser coming in. So that's what I'd expect. And then the blue is this dip that's caused by the backscattered SBS light. So that could be done for this case. Other cases it's useful for is looking at things called side scattering. So the scattered light from this SRS instability doesn't always just go backwards, it can go at the sides. And you can do that by applying this version of upward and downward SRS at these point influx at these side boundaries. And then when you plot it all out, you can see that you get your correct sort of angular resolution that you'd expect.
Excuse me.
Yeah.
Sorry if you've already covered this. I missed the beginning. Is it possible for you to model 2 photon decay, or 2 plasmon decay? Sorry.
Yeah.
Yeah. Is that the cover? Isn't it?
Yeah.
Okay.
Yeah. So I guess you'll see towards the end. I've got a picture where you can see CPD.
Okay.
So that's one diagnostic, and again, you can then do this along the whole density ramp, and you can see, where is my laser being depleted, where is my SBS growing, where is my SRS growing, and so on. And then this is the thing that will eventually be added in EPOCH, the one that you're allowed to use. These things called accumulators. So rather than, like I said, outputting the entire field grid at all the times I need to. So if you want to do this filtering, you're going to have to resolve the laser frequency, which means normally you're going to have to output each thing at something like 0.1 or 0.05 femtoseconds. If you did that, without these accumulator fields, you would end up with about, 50,000 SDF files. It's a bit of a pain. What these accumulators allow you to do is, you could set up your subsets at all these locations, and then instead of outputting, 20,000 or whatever files, you can just, ask it, dump me these files at this time, but accumulate all the data at all these time steps. So it makes, instead of having 20,000 files, you could have 200. Makes your life a lot easier. I've realised I've gone severely over time. So, in terms of like working out key things for your future sort of surrogate models, you want to look at things like hot electrons. I sort of ran through this now, but this can come from your probe, things that Stuart mentioned before. You set up your probe, you can just measure the momentum passing through it. You can then work out your energies, bin your energies and your spatial locations and time points at each of these probes to get some sort of histogram. You can then do some mass averaging to work out your flux, and you get these sort of flux distribution figures from the bottom here in black. If you then fit them with some multi-Maxwellian model, you could do it by brute force and guess, each component of your Maxwellian has a certain population and a certain temperature, and you get this sort of nice multi-Maxwellian fit that fits your data. So this will then basically tell you what your hot electron temperature should be, and you can get some sort of singular estimate, which is useful for a surrogate by doing some weighted average to pick your mean temperature from your posterior fits and your mean fluxes for each of these mean parameters. Again, you could then not average over time. You could leave this as a time varying approach, and you can basically then use these in tandem with your Poynting flux to help diagnose, where SRS is growing, for example. So SRS has a scattered light wave, and you can see in these blue peaks over here, this is where we're recording backscattered SRS light. But at similar times and similar peak shapes, we can see that hot electrons are being produced near this 19% critical. So this allows you to sort of, not only use your reflectivity diagnostic, but your hot electron diagnostic to tell you exactly where your instabilities are growing. And it's useful again if you want to put something into a hydro code. Again, for the sake of time and not droning on, this is basically exactly what Stuart said about how to use probes. But if you're interested, you can have a look at the slides later on. And then, I guess the key thing here is you want to do a lot of Fourier transforms. These are three wave instabilities. They have things which are dependent on phase matching. So all these things live in reciprocal space. So, I haven't got Joel's level of nice experience with software engineering, so SDF X-array might do this a lot better, but what I would do with the normal SDF helper is I just make some big 2D array with all my time points going from left to right. I could then do just a temporal Fourier transform in each direction to get some sort of frequency spectra, and I can see where, what type of LPR waves I'm growing. But then you could also just put this as a 2D Fourier transform both along time and space, and then not only can you resolve, what type of frequency you've got, also what type of wave numbers you've got, and therefore what direction are they growing in, and those curves that lie along them are solutions to those matching conditions. So again, you can solve the matching conditions, see where the Fourier waves grow alongside them, and go, okay, that's SRS in this direction. On the other side, it could be some other instability and so on. Again, a lot of Fourier transforms is the key. You could then do it again, but instead of doing it over all time, you can do something called a short time Fourier transform. I believe that's kind of how, like, if anyone's used the app Shazam, that's how Shazam works to tell you what song you're listening to. But in this case, you basically set a moving window. You set a window size and how many discrete time points you're going to want for your plot, and it hops this sort of moving Fourier transform window along, and that way you can see, at what point you're seeing these frequencies. So this can help sort of diagnose that, like, one instability is happening here at this time, another instability is happening here at this time, so on. And again, these curves come from the matching conditions, so the green is for TPD, and you can see quite a lot of them lie within this TPD range, and then this blue is from SRS. So a lot of it's just detective work, basically. You just solve some matching conditions and see where everything lies. And I promise you this is probably one of the last slides now. But again, it's Fourier transforms again. In this case, this is for if you want to do 2D results. It becomes useful to take, less regular snapshots of the entire grid. You can do things like look at density perturbations or electric fields to have a look at things like electron plasma waves. You can do 2D Fourier transforms and get the whole K space, but you could also do a Fourier transform just along the Y direction. So this way it can have you see again where these instabilities grow. So the blue lines are from this SRS instability, and you can see this, for example, signal here is due to SRS. But then these green lines are from which we create in 2 plasma decay. So again, it helps you diagnose what's actually going on in your simulation. And then once you've done this, you can also use the fact that your initial behavior is defined by linear growth, which means that things like your electric fields and your density perturbations grow in some exponential fashion. You can then use these snapshots to estimate what your growth rate is and plot them nicely. And then the red and the pink curves basically tell you this is what I expect to see if I'm getting convective growth. And if they match like that, you can help diagnose what type of growth you're getting. Yeah, comparison to experiment. It does pretty well at SRS. SBS can be quite problematic because no one really knows the ion temperatures very well. And if you get them wrong, it goes back to the discussion about your ion damping and with the modelling the 2 ion species. I'm just going to leave it there before I bore you anymore and you want to do your research projects. But if you ever do any LPI stuff, all those diagnostics and about 40 others are all on one Git repository that you can use, so you don't have to suffer like me and do them all again. Right, cheers.
Take it away, Tom.
Okay. I don't pay attention. Yeah, not bad, not bad. Okay, so this is essentially the collection of things that we couldn't squeeze into the regular timetable. So it's a list of things you can do beyond what you've been told how to do them. In terms of, we're going to talk about different options for pit codes. A lot of you have used the hybrid code already. We'll talk a little bit about that. But more importantly, from my perspective, I kind of want to sort of try and push for feedback from you guys. This is both in terms of the workshop sort of feedback, because we're definitely doing another one. I'm swindling some money for that, hopefully. And also just in general in terms of where EPOCH's going, what our sort of development, and I say our development plan, it's my development plan. What you guys would want in the code, what features are useful, what features are not. And so that's the rough agenda for the next, it's going to be half an hour, give or take. Okay, so here's the main problem, right? It's that pit codes are very expensive. Their main selling point is they're cheaper than Vlasov codes, and that's certainly true. But the reality is that to really try and study, in particular, well, I've got an LPI image here because that's what we do at Warwick, but if you really want to study sophisticated, complex experiments in probably 2D, if not 3D, you're looking at an awful lot of compute. To give you a rough idea, we're talking a single simulation, we're going to need upwards of 100,000 cores. That's going to run for like a week. And that's going to be one data point in like an 8D parameter space. So we're not going to be able to tell you the answer of the EPOCH, even if you could somehow magically exactly match your laser parameters, exactly match your plasma parameters. I've got the second and third bullet points here are to sort of, what's the opposite of reassure? Worry.
Point out the flaws.
Yeah, it's sort of worry that the two main sort of directions of scientific investment in this country, at least, they're not going to help you. Basically, all compute-driven investment is governed around machine learning and AI at the moment. But as I said, if you've got, all of R2 for a year, you've still only racked up 52 data points in 80 parameter space. I don't care how good your neural net or your Gaussian process regression model is, it's not going to be able to trainable on that. And the third bullet point is, even if you do have some belief that quantum computing will be useful, it's not going to be useful for physics. And those are the two main directions. So we're going to have to do something a little bit smarter. We're going to have to try and come up with some solutions that will help us, and we can no longer rely on scientific software being the main driver of the supercomputers in this country and indeed the rest of the world. Those days have gone, I'm afraid. So essentially, there's what we can obviously do, right, is we want to try and reduce the amount of work our codes have to do. If you look at a PIC code, all of the memory requirements are in your particles, all of the compute requirements are in your particles. The field solver is free, the boundary conditions are a bit fiddly, but they're free. So what can we do? Right? And the obvious answer is you want to reduce the number of particles. There's a problem there, as some of you have probably worked out during the last 2 days, and having sort of overheard various other points, is that you're going to want to have a lot of particles in there to avoid self-heating. Self-heating is essentially this. It's basically a result of the fact your classic explicit PIC code is not energy conserving. And not only is it not energy conserving, it's not energy conserving in an asymmetric way. It's not just going to have your little fluctuations in energy, your plasma is just going to self-heat. This is increasingly bad as you increase density, but it will eventually get you. And there's three things you could kind of do here, right? One is that you could try and address the root cause, which is this energy conservation issue. You can write energy conserving PIC codes. So I've written energy conserving PIC codes. On the next slide, I'm going to tell you why you don't want to go in that direction. So what you really want to do is either reduce the number of computational cells you got, because that's a sort of indirect way of reducing the number of particles you got, or just use fewer particles in general. I will, as I said, one of the things that UKAA looked at when they were looking at designing their sort of compute resources for, well, I guess not really R3, but their next generation of clusters, was looking at energy conserving PIC. As I said, you can do this. There are a number of issues, but crucially what it does do is it conserves energy, so it's not going to self-heat. It can't. However, the problem here is that what you end up doing is you're going to have to construct a very large linear system. That linear system is not going to be particularly sparse. You're effectively going to have a matrix row for each one of your particles, and you're still going to want quite a few particles in there, and that's going to kill your compute. There are other issues, and this is kind of, I guess, a general warning about numerical physics in general, is that you're very rarely going to be able to get rid of one problem and not unearth another. So you can, as I said, you can write the energy conserving PIC codes, but what they don't tell you in the papers, but what is quite apparent when you actually code it up, is that it shits all over Gauss's law. Your charge conservation then goes out the window. So you're just nudging errors around, and eventually that you're going to get some spurious E field generation. So maybe it doesn't self-heat, but your electric field's wrong anyway. So that's why we're going on that route. Okay, so what can we do instead? As I said, we can reduce the number of cells, reduce the number of particles. There is, frankly, nowhere near enough time to explain cylindrical PIC to you or hybrid PIC. So what I'm going to do, in an attempt to be vaguely useful at this time on a Friday afternoon, is explain the motivation for using cylindrical PIC, and then in red down here, this is the bit you want to worry about. Again, there's no free and easy solution. You fix one thing and another thing.
Are you able to send these slides?
Yeah, they're on the GitHub repo. But anyway, so the basic idea is that nearly everything we do is kind of cylindrical, right? Lasers are roughly cylindrical. What we really care about in a lot of plasma accelerators, so a laser wave field is roughly cylindrical. Maybe it bulges out a bit, but and so we're probably not going about this in the most sensible way if we're going to try and solve this on a 3D Cartesian mesh. We're going to try and take advantage of that symmetry by writing what's known as a cylindrical pit code or a quasi 3D pit code. And then, rather than having nx by ny by nz cells, we're just going to have nx by nr. R and X, I don't know what, it should be R and Z. Sure, you made this diagram. Go and look at geometry. Anyway, so you've got a massive reduction in the number of cells here. I mentioned accelerators because this is kind of what it's designed to do, and this is what I would keep in mind. So what this sort of methodology I think is really, really useful for is if you are looking to design a new laser weight field experiment, for example, you don't quite know a whole bunch of parameters. What you can do here is you can then set off, 10,000 of these simulations, and you might have a cat and house chance of getting an answer. You couldn't do this in 3D. The issue, however, is that I wouldn't necessarily be happy if I was refereeing one of your experimental proposals and the simulation side was just a bunch of 2D RZ pit codes. I'd be like, well, have you checked it in 3D? Have you checked it in the actual full pit code? So that's the first sort of warning with this is, yes, you can massively reduce the computational cost from doing large scale 3D pit to doing 2D pit. You would want to go away and check the results. The second issue is that, as I said, this is designed for accelerated physics. What Stuart found is that it's quite prone to our good friend self-heating, and that self-heating is really quite bad for solid conditions, and it's also really quite bad in the axis. That sort of, again, it chimes back to the idea of, sure, go away and do your parameter scans in these cheaper 2D simulations, but you'd want to check it 3D pit. Nevertheless, we have a cylindrical pit code. It is available. I don't know if we've... how easy to find cylindrical pit code? Is it like linked from our web pages, or?
I think it's just in the EPOCH pick GitHub environment, I think. Same place as normal EPOCH and these workshop slides.
Okay. So I guess a quick check. Did anyone know there was a cylindrical version of EPOCH? Not you.
Well, I guess like new.
You can keep your hand out. Yeah. So I mean, I guess consider this an advert, right? Because Stuart wrote it, it's really well documented. There's example of the decks as well, I think.
Yeah.
There's a.
It is available as well.
Yeah, it's publicly available. Go and have a play, but please keep in mind that the points in red, not just the points in green. Okay. We'd be super happy if you guys were picking these sort of extra versions of EPOCH, because otherwise, as you've seen from the last 5 minutes, I can't remember where they are, so they're just not going to get looked after. Okay, so that's one way we can do cheaper simulations. The other way is hybrid pick, and again, this is Stuart's PhD project. The motivation is pretty simple. You can't, well, unless you have a massive computer, you're going to really struggle to simulate a laser-solid interaction. However, the actual laser-solid interaction only occurs over a really small fraction of your simulation domain, right? Because you have your laser that comes in, it's going to hit your aluminium or whatever you're firing it at, and it's going to set up a small, tiny pre-plasma, and then immediately jump to the critical. So the laser's not going into 99.9% of the domain. What you really care about is, I don't think you can turn it off. What you really care about is the hot electrons that are generating this pre-plasma, and then they go into your solid. That's the thing you want to model. And so the way a hybrid pit code works is you replace your laser as your source of energy coming into your domain with some hot electron species. Now, I say some hot electron species, you have to kind of calibrate that. As a decent guess, you're looking at some exponential distribution function. The peak will be given by the peak laser power, and then you've got some efficiency, which is probably quite small, but essentially not. I don't think there's any a priori good guesses for it, right?
Play around with it, I guess.
Yeah, and so And actually, so I didn't want to put this plot of Stuart's on the presentation because I looked at it and I just sort of, well, EPOCH's kind of crap there, isn't it? That's the EPOCH, the blue line here, trying to compare to these fairly large error bar experimental data. But the point is, you can tune effectively you've got an efficiency at how much laser energy goes into electrons, and you can tune that, and maybe you want to tweak the distribution function shape a little bit, and you can then go in and do a really good job of reproducing this. Quite why Stuart didn't include the really good job on the plot, I don't know, you'd have to ask him. And so again, this is kind of my sort of two-level message here, is that there are really good motivations for doing a hybrid pit code for simulating laser soil. It's certainly better than doing with a conventional pit code, but that's a very low bar. However, what you really want to do is to do a full kinetic pit simulation of your pre-plasma interaction. Use that to characterize your hot electrons. Take those hot electrons either as directly from one of the outputs we've got on EPOCH, or just do a bit of pre-processing. Put that into your fluid, into your hybrid code, and then you're off. There are other issues. The first is that this idea we're going to treat this solid as a background fluid. It's not really a fluid, it doesn't move, for example. And so what we're going to essentially do is, yes, we're going to transport these hot electrons through this quote-unquote fluid, and they're going to deposit energy and potentially ionize and create secondary electrons and so on and so forth. But do not sort of fall into the trap of thinking you're doing fluid scale simulations here. If you want to solve something on the time scales and the length scales which you expect serious movement of your target and serious expansion of your target, you're going to have to do something else. I can suggest what to do, but that's even more difficult. There are also some uncertainties in exactly how you treat the sort of transport of these electrons going through your target. The alternative to doing this, since we're on it, would be to do a full fluid simulation with kinetic. Was that a hand up or?
Yeah. I was just wondering if you've got to do the full pick simulation anyway to get the hot electrons, and you're not going to be able to simulate fluid scale problems, then what is like what is the benefit of hybrid pick in
You'd be looking at things like radiation emission as your hot electrons go through.
Okay. Yeah.
Your solid
right. Okay.
is the example
Yeah.
that I think is correct.
Yeah.
Okay. Yeah. There are genuine experimental results you would want to be able to try and simulate of these hot electrons going through your solid. But as I say, it's just a word of warning. Now you can, and I'm kind of maybe pushing this as an option for sort of future EPOCH development, or at least future EPOCH documentation. You can, of course, take that same hot electron model and stick it into your fluid code. Your fluid code needs some modifications, but we've done this for quite a while with hot electron generators like from LPIs. The models are, at least to some degree, relatively well known, and essentially all you have to do is add on a few kinetic species to your fluid code. It's not easy, but it's perfectly doable. The issue with that is that you're probably going to have to start making the other things up. So what you'll find if you launch the hybrid pit code is you're going to see a lot of electron refluxing as they try and leave the domain but get pulled back in. And you can do that in an almost self-consistent way, is it fair to say, hybrid pit?
Benchmarks against 2D pit
Yeah.
for some amount of time. It's mildly robust, but
I like it mildly robust. So you can certainly do it in an almost self-consistent way, in an accurate way in 3D hybrid pick. When it comes to modelling these things if you're just going to put these things in your fluid code, you really are making it up. And probably your best guess is that they're nearly always reflux. Okay, so that's my sales pitch, not a sales pitch, just some thoughts on hybrid pick. If you are interested, read Stuart's thesis. That's got an awful lot of details in. But again, so hybrid EPOCH has its own repo, right?
Yes.
And
So
that,
it has a version that was trying to merge with the main EPOCH. I think that's still in development. And the standalone code that I wrote for my PhD is in a separate EPOCH repository,
Yeah.
which I think is linked to in the paper where we talk about this.
cool. And again, it comes to documentation.
Yeah.
Yeah, excellent. I was going to say I can't really explain any of these things in 2 minutes, but I'll babble for longer than 2 minutes. Again, it's public. Please use it. It makes us feel slightly better about the time we put into these things, and also it keeps the code alive. Okay. So those are your two sort of algorithm options. The alternative is we just need to do more compute, right? That's kind of the. It's not the definite conclusion of those two slides. There are definite use cases for them. There's definite use case for hybrid pick, but you know, the reality is to have a completely robust kinetic simulation tool, we're just going to have to do more compute. Okay. However, and here's the problem. Current and certainly the next generation of HPC facilities are all going to use GPUs, or at least be largely dominated by GPUs, which means we're going to have to do something different. Yes, you can write Fortran code for GPUs. I wouldn't recommend it, and I think it will just die eventually, hopefully. So, as part of a major motivation here is to have a version of EPOCH that is going to be equally performant on x86 or ARM or GPUs or whatever the sort of next generation, possibly heterogeneous compute facilities are looking like. And this is kind of how we've ended up with EPOCH++. Again, show of hands, who knows about EPOCH++? Yeah, I see. That's better than I thought. I say better than I thought because EPOCH++ is currently sitting in a nice private repo that only few people have access to. That will probably remain private for a while, but if you would like to be a beta tester, please email me. Maybe emails can be on the next slide. Again, users are really the thing that keeps codes alive. I looked at, like, if you look at the list of codes that I've probably made commits to in the last week, there's like at least a dozen codes. And if I'm not going to be getting email pings and GitHub issues and GitHub pull requests, these things will just disappear. They're going to fall off the page and go. So other useful things or things to point out about EPOCH++ is we don't have 3 code bases anymore. That was a nightmare. It doesn't matter how skilled you are at applying patches and hacking around diff files. Maintaining 3 lots of code was a real pain. So that's not all being condensed down into a single code base. So you haven't got EPOCH 1D, 2D, 3D anymore. It's just EPOCH++. The second bullet point, I can think of at least one person in the room who doesn't necessarily like this and one person who does. We've, at the moment, got a standardized sort of interface to physics packages. What I mean by that, I can explain by, I guess, the counter example of what's currently in EPOCH. If you've ever tried to add a new physics package to EPOCH, be it Bremsstrahlung or collision ionization or some quirky QED model, you're sort of on your own. You're going to have to go through, you're going to have to sort out all the sampling, how you're pairing up species, what you're going to do about arbitrary weighted particles, how you're going to sample from different distributions. All these things are essentially all being done for every single physics package. But there's, because EPOCH's kind of like grown and evolved the last 20 years, there's no sort of standardized interface. And what I've pushed for in EPOCH++ is to try and sort of put a halt to that. And the idea would be that, I guess in the simplest possible case, you know, if you wanted to go away and collide 2 particle species and you know the products, you know what particle it produces, so it says recombination, you want to collide, for want of a better word, you want to combine your electrons with your ions. you know what the product is. It's going to be a lesser charged ion, and you probably know the cross sections. That should, in my mind, be all you would have to provide as a user / wannabe developer. You shouldn't have to worry about what do you do about arbitrary weighted particles. We've also added a sort of Python interface / Python ability to control the simulation. Just an attempt to be sort of vaguely modern, basically. GPU support is the major sticking point. That's why you haven't seen the public release of EPOCH++ yet. It's kind of like it's right there at the top of the slide because that was one of the, if not the main motivation for rewriting EPOCH, and it's just the one thing that I think we need to do before we can push out public release. The other thing worth mentioning is that a lot of work from Stephen Wright's group here has gone into the I/O. You saw today from Ben the terabytes and terabytes of data that we produce, even with highly optimized choices of probes and subsets and accumulators and all that. You're still going to produce masses of data potentially. And so I think that the I/O on is at least an order of magnitude faster, if not even better. So you no longer have to stop your simulation 3 hours before the wall clock time to write that final output. Okay, so that's, I think, the EPOCH++, I would argue, is the one you really care about of the 3 things I mentioned. Right, as I've said, if you're not using codes, they're going to disappear. You know, in the best case scenario is they're going to sit there for a year. Someone will pick it up again, at which point you've upgraded your compilers and the whole thing falls over again. In the worst case scenario is you lose the documentation, no one knows how to use it. So what I would find most useful is please don't hold back from opening GitHub issues. If you want to contribute to the code, they are all nominally open source, even the private ones. You've still got an open source software license. Don't hold back from putting in a pull request. It could well be that you're going to put in a pull request and I'm going to tell you that that's an awful bit of code, but I will also try and help you fix it. Again, don't hold back on what I've described as annoying emails. I think that the assumption is that, and I think this is probably particularly true of new PhD students, they're sort of like, I don't want to bug my supervisor too much, or I don't want to bug XYZ academic. The worst thing that happens is I just ignore your emails, I'm busy. I will eventually get to them. And again, if I'm not seeing these email notifications, I'm not seeing these GitHub notifications, it's just going to disappear because frankly, the other 11 codes that I'm working on, their users are noisy, they are shouting me, they are constantly nagging me to do stuff, so just join in basically. I have also mentioned, please give us feedback on this workshop, what worked, what didn't. It is, for me, I found it really encouraging to see so many people here. I think it's been a couple of years since I've done an EPOCH workshop, and I think we basically hit capacity numbers for most of it. Yeah. So let us know what worked, what didn't. We can improve. Keep this in mind in your research groups when, this time next year, you probably don't want to do one of these things again, I'm guessing, but there's going to be new first year PhD students. Tell them to come along, hopefully say good things about us. I've got a 10th slide apparently, so let's see what's on that. Okay, so here's the future, and I think there was like a 15-minute time slot at the end where we were going to talk about feature requests, but at the very least, think about it for the next half an hour and then come back to me. Our cylindrical and hybrid EPOCH, they are public, they're available, they're documented. Please go away and use them if it's relevant. Don't use them if it's not useful for you, but if you are looking at doing some laser weight field work, then go away and try cylindrical EPOCH. If you're looking at simulating laser solid stuff, try hybrid EPOCH. I would really like to see people start picking up EPOCH++. If you feel like you are either wanting to get involved in the sort of C++ side of things, or you feel sort of relatively confident enough to even maybe compare Fortran EPOCH to C++ EPOCH, pop me an email. If you're just curious, pop me an email. we can keep adding people. That's not really a problem. And my suspicion is whenever you add users to codes, you're going to see issues pop up. You're going to find bugs. My suspicion is that the layer of bugs that I'm sure exist in EPOCH++ are going to be super simple to solve, but until someone's tried to do something like, oh, I've specified my laser in terms of wavelength rather than frequency, and it doesn't work, or something like that, right? I'm probably not going to spot that. So please, if you do have just even spare half an hour, pop me an email. I'll add you to the repo, pull down the code, check it builds. That's useful. Things that I'm kind of interested in is kind of talking about interfacing EPOCH with other codes. The bottom bullet point here is sort of EPOCH fluid codes. Here is this idea of, if I go away and take one of Ben's LPI simulations and I measure the hot electron population generated from SRS, I might then want to go and pop that into my fluid code, see how that impacts things. Similarly, I would like to see, or I would be happier seeing, a stable instruction and documentation of how to use hybrid EPOCH and also how to combine conventional EPOCH to hybrid EPOCH. Because it's one thing for me to tell you, you definitely need to go away and do these full pick simulations to characterize hot electrons, but I probably can't right now tell you how you take those hot electrons into hybrid EPOCH. So again, just start nagging, start asking questions. And the other thing is this is a little bit niche, but it goes within the sort of group of interfaces with the codes. We're talking about doing some EPOCH G4 simulations. The idea here, again, it comes back to a lot of things like plasma accelerators. If we're going to say have some TSA generation protons, you might then want to chuck them at a secondary target inside of your experiment. What I'm sort of aiming to do is, again, write a custom event generator in G4, which isn't too bad. It's going to be like probably 100 lines of C++. That's not the big thing. What the most useful thing is, again, having that documented, stable, this is how you take a proton spectra from an EPOCH simulation, put it into G4, and fire it into water, for example. There's actually a surprising number of people that do that, because it's essentially, water is essential flesh, right? And that's kind of how they test a lot of proton therapies. Other useful things exist too, but again, it's the real emphasis here is probably working out on what, if any, of these things are you all interested in. I think we've had a lot of talk from on the platform with First Light about combining EPOCH and EPOCH hybrid, or maybe EPOCH fluid codes. So yeah, let us know. If it's not clear how to do something, let us know. That's fine. You don't have to struggle on in silence. That's really not really what you're supposed to be doing. You're supposed to be going doing interesting science, not scratching your head because I haven't been bothered to update the documentation. We've talked about future workshops. The other final thing to keep in mind is I'm kind of pushing EPOCH towards a regular release schedule rather than the sort of ad hoc flurry of releases and then silence for 9 months that we have at the moment. The idea here would be that somewhere on the EPOCH webpage there's this is what we're planning to do in the next 3 months. And again, that's your chance as users to send me an email and say, actually, I think that linear Compton scattering is more important than linear bright wheel, which probably is. Maybe prioritise that. And again, we can then actually adapt our sort of release schedule and our development plans according to you. I think that's all I had to say, Joe. I don't know how I waffled long.
10 minutes over, yeah.
Yeah, that's not bad. So in that case, I guess we're sort of moving straight on to the virtual, in-person laptop poster sessions. So yes.
Where can we give our feedback again?
So if you go to the EPOCH Pick website on the Quick Start Guide, where the EPOCH workshop timetable exists at the moment, on there at the top of that you should now have a new small paragraph there with a link to a new Google form.
Oh, great.
Yes, thank you.
Is that anonymised or?
Yeah, it can be anonymised. If you have specific feedback and you want to feed that back to us and then talk about this more, there is a box you can fill in at the end of that if you'd like to do so as well.
Yeah, we'll failing that. Just
Is it requesting a password about
Sorry?
your ID or something?
No, I turned off the whole thing, otherwise it doesn't work for people without a Google account.
Yeah.
Just a quick note on cylindrical epoch,
yes.
which is unfortunately at the moment SDFX rig does not work with cylindrical epoch because of how cylindrical epoch's set up. So that's just a little FYI, sadly. It works with hybrid, not with cylindrical yet.
Sounds like you've got some work to do there.
Sounds like I need to find some time.
I can already envision that being a paper. To be honest.
Oh, you don't know.
Okay, that's my words.
Thanks,
Stuart, do you want to say some inspirational words?
Yeah, I just wanted to know for the poster session how this is actually going to work. I suppose we could do one of two things. We could actually go ahead and do the virtual poster session. Just show of hands, who would have something that they can show on a laptop screen that they've been working on for this? Yeah. Who would rather spend the next half an hour finishing off and getting some support from us coming round to help finish off what they're doing?